Okay, guys, we are returning back to second part of our lecture 4, and we finished at the point where I explained you how to build inverse to 2 by 2 matrix, right? Now, uh, before we start talking about how to build inverses to bigger matrices, let's discuss why do we need inverses? Well, let's imagine that we have, like, I'm going to label this as use of inverses. Well, this is not only one use of inverses, but one use of inverses which we can apply right now. Imagine that you have a matrix equation or a linear system. For example, it's going to look like this. X plus 2y equals 1. 3x plus 4y equals 2. Linear system, right? Let's convert this linear system into matrix equation. First, matrix of coefficients. 1 coefficient, then 2, then 3, and 4, right? Then we multiply it by unknown column x, y, right? If you just regular multiplication of this matrix by x, y, we are going to get x plus 2y. It's going to be 1 by x, 2 by y. And if you make it equal to the column of the right side, 1, 2, we are going to convert our linear system into matrix equation, right? If we label this matrix as A and the column was x and y as x, like unknown, and this right side column as B, we are going to get matrix equation in a shorter way as AX equals B, right? Well, if you treat it as like just a product of normal numbers equals to a third number, what would be solution for x? If it was just a linear equation. Well, solution for x, generally speaking, would be b divided over a, right? We just had a linear system in normal numbers. We know that we don't have division for matrices, right? But division by matrix, it's actually multiplication by inverse. So maybe we can solve this linear system same way we work with a linear equation. Imagine that you multiply left and right side of this equation by inverse. I'm going to use green. So I'm going to multiply here by A inverse and here by A inverse. Well, of course, if we consider that A inverse exists, if matrix A is not singular, right? What are we going to have in this case? A and A inverse is going to produce identity, right? Multiplied by X, and you get A inverse multiplied by B. Or X is going to be equal, actually, A inverse multiplied by B, because identity by X is just X. So basically, guys, if we do know somehow inverse of matrix A, we can just multiply it by the right column, and we are going to get the answer, x and y. Well, let's check if it works. Remember, in the beginning, or like at the end of the previous part of lecture 4, I was considering matrix A 1, 2, 3, 4 as like my example matrix to build inverse. If you compare it to my matrix in this example was equation, that's exactly the same one, right? So I already know inverse because I kind of calculated that inverse at the end of my first part of lecture 4. Why don't I try to use it? So my x, my column x, which is actually what? Not just x, but x, y, 2 unknowns, it's going to be equal product of matrix A inverse, which is kind of this one, which I already kind of calculated ahead of time. Minus 2, 1, minus, actually that's not minus, that's just plus 3 over 2, sorry, 3 over 2, and minus 1/2. And I'll need to multiply it by b, column of the right side, which is 1, 2. Oh, let's just calculate what it's going to give me. Not difficult to multiply because we just have one column here. So basically there are going to be just two expressions. Minus 2 by 1 is minus 2 and 2 by 1 is 2. So minus 2 and 2 is going to give me 0. Good. So my first element is 0. My second element, 3 over 2 by 1. 3 over 2 by 1 is going to give me 3 over 2. Minus 2 by 1 over 2, which is going to give me minus 1. So 3 over 2 minus 1 is going to give me 1 over 2. Okay, so that's going to be my answer. Solution for this system of equations. Just to make sure, we use a very new method to solve it, right? Maybe we should check back if it's going to work for our system. So what I'm going to do, guys, I'm going to write down that my solution here is x equals 0 and y equals 1 over 2. I'm going to plug in these two answers into my original linear system. No matter which method I used, I'm supposed to fit my solution and it's supposed to make my system, turn it into a system of true statements. X equals 0, 1, half. 0 plus 2 multiplied by 1 half, which is 1, equals 1. Now, 0 plus 4 over 2, which is 1 half, right? It's going to be 2 checks. So this is my solution. And I got it. So this is one of the very good uses of inverse matrix. If you do know inverse of your matrix A, you don't need to solve the system. You can actually just multiply your right side by that inverse and get the final answer. It's very good. Now, what else do we need to know about inverses? There are some rules of inverses or products of matrices with inverses, which we are going to discuss now. Let me move this out. So we're going to do the theorem. And the theorem is going to tell if we do have two invertible matrices of the same size. Theorem. If A and B are two invertible square matrices of the same size, then inverse of a product of these two matrices is going to be equal product of inverses of them in opposite order. So what I'm trying to say, if A has A inverse and B has B inverse, then the product of A and B is going to have inverse, and we can calculate it by multiplying inverses to A and B. It's going to make our life a little bit easier. Instead of like finding the product first and finding inverse to that product, we can just multiply two inverses. Of course, if we know them. I'm going to prove this theorem doing case analysis. So first, I'm going to write down what means that A and B are invertible. A invertible means that A by A inverse equals A inverse by A equals identity, right? Same for B. B by B inverse equals B inverse by B equals identity. So this is given. Now, need to prove that AB product multiplied by their inverse. And we are stating that inverse of AB, this one, inverse of AB equals to this expression. B inverse by A inverse is equal to identity. So if we kind of show this, then we can label this as inverse of this. So product, and this is its inverse. Also, the second statement is inverse multiplied by AB equals identity. Remember that inverse has two sides, left and right. Guys, I'm thinking that I'm going to do one side and I'm going to ask you to do this one at home, okay? At home. Both sides must be proved to conclude that. I'm going to do this part. I'm going to use associative property of multiplication, which is going to tell me that this expression over here can be written as AB, B inverse by A inverse, and can put parentheses over here. I know that this expression is equal identity because B and B inverse is equals to identity. So I'm going to have A by identity by A inverse. And I know that this one is still A because identity is multiplied by A is A. I have A by A inverse. And I know that this one is equal inverse because it's given that A has inverse, means that it's going to be identity. That's it. I proved my first statement. So I proved that my left side is equal to my right side. And I'm going to ask you to do the second part at home. You probably see already how you can use associative property of multiplication, change, rearrange parentheses, and prove everything. Okay. So, well, it's a good theorem. I don't know how many times we are going to use it, but like at least we are going to use it once when we prove something. Now, maybe we should talk about like properties of the powers of the matrices. What are powers of the matrices? We are going to just do some definitions here, and after that, I want to change the color. I'm just tired of blue. Powers. Matrix. So we are going to start with definitions. Matrix A to the power of 0. We are going to consider only square matrices. I'm going to label it if A is n by n square matrix. So 0 power of the matrix is going to be defined as identity. So all other powers, what is going to be the first power of the matrix? Well, that's matrix itself. What is going to be the square of the matrix? It's matrix multiplied by itself. And all other powers, power of n, is going to be a product of matrix A n times by itself. Okay? Now, if A is invertible, has A inverse, then we can define A to the negative power of n. What that's going to be? It's going to be A inverse to the power of n, or product of n A inverses. A inverse by A inverse by A inverse and n of them. Okay. Why do we need them? Well, actually, guys, know that for real numbers, we can have polynomials. We also can have polynomials for matrices. Imagine that we do have a polynomial, just a regular polynomial. Let's label this matrix polynomials. Imagine that we have a regular polynomial p of x, and it's equal a0 plus a1x plus a2x squared, and somewhere at the very end, an x to the power of n. It's just a regular polynomial. Now, imagine that instead of x, we are going to use a matrix A. Of course, a square matrix A. What are we going to have? Well, because we are going to have addition here, we cannot add just a number. For real numbers are just a number, scalar. We cannot add a scalar to matrices. We are going to have matrices over here if we plug in A instead of X. So we're going to turn this A0 into matrix 2 by multiplying it by identity. For the rest of the coefficients, we are going to keep them, and we are just going to use powers of matrix A. And the last element is going to be an x to the power of n. Coefficients are going to be just scalars, regular numbers, and a powers are going to be powers obtained by the rule. And this one can be treated as a to the power of 0, the first element, because actually what we have here is x to the power of 0, right? We do know that a to the power of 0 is identity. Okay? So this is how we deal with polynomials. We are going to see polynomials a couple of times in the future. Now, guys, let's do one more definition. And I think for this section, which is extremely long, it's going to be the last one. Transpose matrix. Okay, guys, if you have any matrix A, we're going to define a transpose matrix to it. Or maybe we defined it already, right? I was explaining you that the transposing of the matrix is writing down matrix like using columns instead of rows. But let's kind of review it. So what is A transpose of matrix A? If matrix A consists out of elements A, I, J, then transpose matrix A transpose is going to consist out of elements A, J, I. So basically, you are going to switch positions, rows, and columns in your matrix, or you are going to switch indexes in your matrix, and this way is going to build a new matrix, right? Some properties of transpose matrices. We're going to start with the first property. First property, if you have a transpose matrix and you do one more transpose on it, well, we expect to get matrix A back. Well, if you look at this definition, transpose is going to switch indexes to Ji, right? But when you take transpose one more time, you are going to switch indexes one more time, and that's going to be Aij again, which is going to give you original matrix. So double transpose is going to produce original matrix. Well, there are some properties of transpose which are about like addition of two matrices and transposing, which are going to be very easy and we're not going to prove them. So if you do have two matrices and you add or subtract them and take a transpose of the result, you can actually take a transpose of like each matrix first and then add or subtract results. We're going to skip proof of this. And also, if you have a product of scalar by matrix A and you want to transpose it, well, you know, you can always take scalar outside of transpose. Well, next property is going to be a little bit more complicated. If you do a transpose of a product of two matrices, imagine that you have a product of two matrices. What is going to happen? Well, if you do a transpose of a product, you are going to have a product of transposes in reverse order. My T doesn't look very nice. Let me write it down better. Why does it happen? I'm going to prove it a little bit. This property, I'm going to prove. You will not need to prove it yourself, but like I'm going to just show why it works. So when we do the product, of matrix A and B, we are actually to get element of the product. We are going to take one row of matrix A, which is going to be like I row, right? So it's I1, A, I2, and A, I don't know, N, and multiplied by the column of matrix B, which is going to be a J column. So it's going to be B, J1, and B, Jn to get the result, right? Which is going to produce this product. A, I1 by B1, J, and I put J first. I'm sorry. That was not good. B and J, B and J. Okay. And B, A, I2, multiplied by B2J and all these elements, right? It's going to produce element Cij. If you transpose it, it's going to become element Cji, right? And to get element Cji, which is going to be the same number, right? It's going to change position. Indexes ij are describing position of the element, but element itself is going to be the same number. To do the kind of same number, to get the same number, we will need to multiply j row by I column, but keep the numbers. So what does it mean? Well, if we go backward, we are going to have B1j by A, I1, and all of these elements. But to change positions of I and J, we will need to write it down differently. We will need to write down the column first, B1J, and the row second, A, I1, A, I, N. If you do this, yeah, the indexes are not going to be, for these ones, are not going to be sitting in the right place. But if you kind of multiply it this way, it's going to give you the same product, right? But you turn this one into row and the first one, which was row, into column. Now, if you put index I after j, it's going to become like column, like we used to have it, like column I. And here, if you put index j first, and then 1, 2, 3, 4, n, you are going to have the row of j. But what does it mean? If you switch indexes here, it means that you are going to turn matrix B into transpose. So it's going to be B transpose. And if you switch indexes here, it's going to turn matrix A into A transpose. So, well, that's basically why you have the product of transpose in opposite direction. Again, because when you switch the positions, you are going to multiply the same numbers, but they are supposed to become not columns and rows, but rows and columns. Well, that's going to be a transpose, kind of how to do a transpose of the product. The last theorem today is going to be application of both inverse and transpose to a matrix theorem. If A is invertible, then A transpose is going to be also invertible, and inverse of transpose is going to be transpose of inverse. It looks a bit crazy when you see it as a one short formula, but the idea is you have matrix A. We can find inverse of it. Now, if you do transpose of that matrix A, inverse of that transpose, it's going to be just transpose of inverse, which you already have. So you don't need to repeat actually finding inverse. You just can take your old inverse, transpose it, and that's going to produce a inverse of transpose matrix. That's what the formula tells. You turn matrix A into transpose and then take inverse. The result is going to be same as you take inverse of A, original matrix, if you do know that, and just transpose it. Makes your life a little bit easier. I'm going to prove this theorem, and that's a short theorem, so I want you to probably memorize it. So, what I'm going to do, guys, I'm going to prove it using the definition of inverse. Definition of inverse tells us that if A transpose has inverse, then that inverse must be multiplied by regional A transpose. It's supposed to give identity, right? Well, we know, or we assume, that it's supposed to be equal to this. We don't know yet, but we are kind of thinking that the inverse of transpose is equal transpose of inverse. So we're going to write it down over here. A inverse transpose. Going to multiply it by A transpose. And instead of writing down identity, I don't know is going to identity or not, we need to prove it. I'm going to first work with this statement. I know that from previous theorem that two transposes can be converted into one product and transpose. That's what I'm going to use. I'm going to write down A by A inverse and then transpose. Why did I change positions of A and A inverse? Well, because the theorem actually tells me that if I open these parentheses, I have to change positions of the matrices and the result. And that's what I'm doing, right? What I do know about the matrix inside of the transpose, I know that it's identity. Why? Because I know that A inverse is inverse of A and the product of them is supposed to be equal identity. And what is transpose of identity? Well, of course, it's identity itself, because for identity, it has all zeros in all positions except diagonal positions. And when you do transpose, diagonal positions are going to have indexes of elements 1, 1, 2, 2, 3, 3. And if you change position of 1, 1, it's still going to be 1, 1. So diagonal elements are not moving while you are doing transpose. Okay, so you remember that this is only half of the proof. A second half of the proof is I'm going to label 1. A second half of the proof is going to show that A transpose multiplied by A transpose inverse is equal identity. Guys, can you do this home? Use this one, put it here, combine it together into one expression and get identity. That Yeah, for right now, guys, we need to prove both sides of multiplication to prove that something is inverse. Eventually, we are going to prove a theorem which is going to allow us to do only one side. But until we prove that theorem, we are going to prove both sides. Okay, and this theorem concludes my lecture. Now, guys, I want to tell you what I want you to kind of memorize or pay attention from this lecture, because there are some important theorems. I'm going to go through the whole notes of my lecture. Let me turn it. And what I want you to kind of learn, we proved some theorems. You don't need to prove the theorem about reduced row echelon form, because there is like the proof is very, very brief. But there is a theorem, maybe I should highlight it. There is a theorem over here about like uniqueness of inverse. I want you to memorize it and to put a check mark. What else? That's for examples. Well, I want you to memorize the formula for inverse of 2 by 2, but I think you kind of understand it yourself, right? Also, I want you to memorize this theorem. So theorem number 2, to label it number 2. And also, I want you to memorize this theorem number 3. Maybe I should have some numbers label numbers. Let me write 3. And this one is 2. And where is my number 3? Sorry. And theorem. So I want you to memorize 3 theorems from this lecture. These theorems are very nice ways to prove stuff in linear algebra, and we are going to kind of use them in exams. I'm going to check one of them on the quiz, maybe both, maybe 2. The rest, you just kind of, there are examples, but they're still kind of important and necessary. For the theorems, I want you to memorize them. Okay? Okay, I think that's all. I did prove this one also, like number 4 property, but makes no sense to memorize anything here, because this is just a very simple like imagination. You imagine rearrangement of rows and columns, and the answer comes right away. Okay, I think that's all for this section 1.4, and please do your homework. See you in class.